Welcome back to the deep dive. We are doing something a little different today. Usually, when we talk about infectious diseases on this show, we're talking about the invisible enemies. We're talking about bacteria, viruses, things you need an electron microscope to see. But today
Today is different.
today we are talking about monsters.
Biologically speaking, yes. We are absolutely entering the realm of the macroscopic. We are leaving the world of single cells and entering the world of complex animals that have decided to live inside of us.
And we are talking about organisms that don't just infect you, they inhabit you. I mean, they build structures inside your organs. They can grow to the size of a grapefruit. We're talking about helminths. Worms, and specifically the pharmacology, the chemical weapons we use to kill them.
And this is such a fascinating area of medicine because it presents this unique challenge. When you're treating, say, a bacterial infection, you are fighting a prokaryote.
Totally different kingdom of life.
It's a completely different biological system. Bacteria are, well, they're alien to us. But a worm is an animal. It's a eukaryote. In the grand scheme of evolution, it's our cousin.
Which brings us right to the central tension of this whole deep dive. How do you design a poison that kills the cousin sleeping in your liver without killing you, the host?
Exactly. It is the search for selective toxicity. That is the phrase you really need to keep in your head for the next hour.
Okay.
And to guide us through this maze, we've got the heavy hitters of pharmacology on the table. Goodman and Gilman's The Pharmacological Basis of Therapeutics, specifically the chapter on chemotherapy of Helminth infection.
Deep dive Bible.
And of course, Katzo and Trevor's Basic and Clinical Pharmacology, the chapter on pharmacology of the antihelminthic drugs.
So as we usually do, we're going to use Katzung for that clinical scaffolding, the what do we do, and then lean on Goodman and Gilman for the really deep mechanistic why does it even happen.
Exactly, a map and a microscope.
But before we get into the molecules, I want to ground this. I want to start with a case study from the source material that, frankly, it gave me chills. It's about a 29-year-old man from rural Peru.
The shepherd case. It's a classic clinical presentation that illustrates exactly why this field matters so much.
So let's just paint the scene. He walks into a clinic. He's got a fever, he's got abdominal pain, tenderness. The doctors run the standard physical exams, and it looks for all the world like appendicitis.
And that's a reasonable guess, right?
Totally. In a young male presenting with right lower quadrant pain and a fever, you assume appendix. That's the horse, not the zebra.
You'd be negligent not to think of it first.
So they take him to surgery. They go in, probably laparoscopically, but when they get inside, the appendix, it's not the main event, not at all. They find a mass. And not a small one. We were talking about a cyst in his liver that measures 10 by 8 centimeters.
Just pause and visualize that for a second. That is the size of a large grapefruit. It's not just sitting there. It's displacing liver tissue. It's pressing on the biliary tree. It is massive.
And then the history fills in the blanks. His family works with sheepskins.
There it is.
And his father and his sister had similar abdominal masses removed in the past.
And that triad sheep, a rural setting, a giant liver cyst, it points to one thing and one thing only.
Echinococcus granulosa.
Hydatid disease. This isn't a bacteria multiplying. This is a tapeworm larva that has literally built a fortress inside his liver.
And that fortress is pressurized. I mean, if the surgeon so much as nicks that cyst and it bursts.
Oh, it can be catastrophic. The fluid inside is highly, highly allergenic. If it spills into the abdominal cavity, it can cause immediate anaphylactic shock.
So he could die on the table from an allergic reaction.
Instantly. And, as if that's not bad enough, it seeds the rest of his abdomen with thousands of new larvae. It's an incredibly high-stakes situation.
So this really sets the stage. We aren't just giving a pill to lower a fever. We are trying to chemically dismantle a complex, multicellular organism that has integrated itself into our own tissue.
That's the challenge.
So today we're going to break down the 4 major classes of weapons we have. We've got the skeleton breakers, the paralytics, the calcium flooders, and what you call the immune painters.
It's a diverse arsenal for a very diverse enemy. And we need to explore how each one exploits a specific weakness, a chink in the armor of these giants.
Okay, let's do it. Let's start with the first class, the benzimidazoles.
Right.
This includes drugs like albendazole and mebendazole. If you look at the chemical structure in Goodman and Gilman, they look deceptively simple. But their mechanism is about destroying the fundamental architecture of the worm.
Right. To understand benzimidazoles, you have to stop thinking about organs and start thinking about cells. Every single cell, whether it's yours or worms, has an internal skeleton.
It's a cytoskeleton.
The cytoskeleton. And it's made of microtubules. These are long, hollow tubes. They act like the steel girders of a building, giving the cell its shape. But they are so much more than just static beams.
They're active, right?
They are the logistical highways of the cell.
Okay, explain that. Logistical highways.
Well, in a cell, things like nutrients, glucose, organelles, they don't just float around randomly. That would be way too inefficient. They are physically carried. They are transported along these microtubule tracks by little motor proteins.
So the cell is a busy factory, and the microtubules are the conveyor belts moving all the raw materials around.
Precisely. Now, these tubes, these conveyor belts, are built from a protein called tubulin, specifically alpha and beta tubulin.
Okay.
Think of them as Lego bricks. The cell is constantly snapping these bricks together to build new tracks where they're needed and pulling them apart to recycle them. It's this incredibly dynamic equilibrium.
Always building, always tearing down.
Exactly. And now, enter the benzimidazoles.
Here comes the drug.
The drug, albendazole, for instance, binds specifically to the beta tubulin of the parasite. And what it does is, it caps the end of the microtubule chain. It prevents the worm from adding any new Lego bricks.
But the cell is still trying to break down the old ones, right? Because you said it's a dynamic process.
That's the crucial part. The disassembly continues, but the assembly just stops cold. It's like a railroad crew that is tearing up the tracks behind the train, but has suddenly stopped laying any new tracks in front of it.
Eventually, the train runs out of track.
The tracks just vanish. The entire cytoskeleton dissolves.
And if the conveyor belts disappear.
The logistics of the cell collapse completely. The worm cannot transport glucose into its cells. It can't move secretory granules. And crucially, if you look at the deep biochemistry in Goodman and Gilman, this disruption also uncouples oxidative phosphorylation.
Which is the cell's power plant.
So the worm runs out of energy. It effectively starves to death and loses all its physical integrity. It's a slow metabolic death. The worm literally falls apart from the inside out.
Okay, but here is the selective toxicity question again. I have microtubules. You have microtubules. Everyone listening has microtubules. Why doesn't albendazole dissolve my liver cells? Why isn't it dissolving the patient's skeleton?
It's a game of affinity. The drug binds to nematode or worm tubulin with a much, much higher affinity than it does to mammalian tubulin.
How much higher?
Orders of magnitude. It's like a key that fits the worm's lock perfectly, but it just sort of jiggles around loosely in ours. It doesn't quite engage.
But it's not zero affinity for humans, is it?
No, it's not zero. And that is exactly why at high doses or with very long treatment courses, we do see toxicity in humans. It tends to target our most rapidly dividing cells because those cells need microtubules to pull chromosomes apart during division.
So you're talking about bone marrow, hair follicles.
Exactly. We see bone marrow suppression, neutropenia, anemia, pancytopenia, because our bone marrow is one of the most active microtubule-dependent tissues in our body.
Which is why, if you're treating that shepherd for 3 months for his liver cyst, you're not just sending him home with a bottle of pills.
Absolutely not. You are checking his blood counts constantly. You're monitoring his liver enzymes. It's a manageable risk, but it's a very real one. We are walking a tightrope between killing the parasite and harming the host.
Okay, so within this class, there's a massive practical difference between the two main drugs, mebendazole and arbendazole. And the text really emphasized that this difference is all about where the drug ends up in the body.
This is probably the single most important clinical decision point for this entire class. You have two drugs that work the same way mechanistically, but their pharmacokinetics, how they move through the body, are polar opposites.
So let's start with mebendazole.
Mebendazole is the stay-at-home drug. You swallow the pill, and about 90% of it just stays in your gut. It is very, very poorly absorbed into the bloodstream.
Which is like a failure, right? Normally you want drugs in the blood so they can get to the infection.
Context is everything in pharmacology. If the enemy is in the gut, you want the weapon in the gut.
Right.
If you have a child with pinworms or a massive ball of Ascaris roundworms living in the intestine, mebendazole is perfect. It reaches these incredibly high concentrations exactly where the worms are, and because it stays out of the blood, the systemic side effects for the kid are almost zero.
So it's like a localized carpet bombing. You just hit the gut, you spare the rest of the body.
Perfectly put. But now go back to our shepherd from Peru. His worm is in his liver.
A drug that stays in the gut is completely useless to him.
Totally useless. He needs the drug to travel. He needs to cross the intestinal wall, get into the bloodstream, and make its way to the liver.
So for him, we use albendazole.
So we use albendazole. It's also fairly insoluble, but it's absorbed much better than mebendazole. And here's the life hack that every medical student memorizes and every single patient needs to know.
Let me guess. You have to take it with a fatty meal.
You have to take it with a fatty meal. And we aren't talking about a salad with light vinaigrette.
We're talking pizza, a cheeseburger.
A cheeseburger, full-fat yogurt, peanut butter, a big glass of whole milk. The fat stimulates bile production, and the bile salts help to solubilize the drug. It can increase absorption by up to 5-fold.
5-fold. That is a massive variable. That's not a small tweak.
It is the difference between a therapeutic dose and a placebo. If you take albendazole with just a glass of water on an empty stomach, you are essentially underdosing yourself so significantly that you might not get enough drug into the blood to kill the cyst.
That's a critical piece of patient education.
It's everything in tissue infections. So once albendazole gets absorbed, the liver rapidly metabolizes it into something called albendazole sulfoxide.
And that's the active weapon.
That is the active weapon, and that molecule is brilliant at distributing into tissues. It gets into the liver cysts, it gets into bone, and crucially, it crosses the blood-brain barrier.
Which brings us to the other nightmare scenario that the chapters talk about, neurocysticercosis.
The pork tapeworm, Taenia solium. This is a fascinating and just tragic life cycle. If you eat undercooked pork with the larvae in it, you get a tapeworm in your gut. Annoying, but manageable.
But that's not the dangerous part.
No. The danger is if you ingest the eggs of the tapeworm, usually from fecal contamination on food or unwashed hands. The larvae hatch, they migrate out of the gut, and they can end up in the brain. They form cysts there.
And the text says this is one of the leading causes of adult-onset epilepsy in the developing world.
It is. So now you have a patient who is seizing because they have a living worm cyst in their brain. You need a drug that can penetrate that fortress. Mebendazole can't do that effectively.
But albendazole can.
Albendazole can.
So mebendazole for the gut, albendazole for the tissues in the brain. That's a really clear distinction.
It is.
Now, the pharmacology gets even trickier here. Often when we're treating these brain cysts, we give steroids at the same time, something like dexamethasone. Why do we do that?
It's a great question. Because when you start to kill that worm in the brain, it doesn't just vanish. It dies. It breaks apart. And it releases all these antigens.
And the immune system freaks out.
The brain swells in response to that inflammatory signal. And brain swelling, edema, is incredibly dangerous. So we give high-dose steroids to dampen that inflammation, to keep the brain from swelling.
Right. But drugs interact.
They do. And here is a fascinating and really fortunate interaction noted in Katzung. Steroids actually increase the plasma concentration of albendazole's active metabolite.
Wait, they help?
They work together. The steroid keeps the swelling down, and it boosts the level of the killer drug. It's a perfect partnership.
That's a happy accident of pharmacology. We'll see later that's not always the case for these drugs.
No, it's a very specific advantage of using benzimidazoles in this particular context.
Okay, before we move on, I want to touch on pregnancy. The texts are quite cautious here.
Very cautious, and for good reason. Benzimidazoles are known teratogens in animals. They cause limb defects and other developmental problems.
Which makes sense, right? Yeah. If you stop microtubules, you stop cell division. An embryo is nothing but rapid cell division.
Exactly. So in the first trimester during organogenesis, it is an absolute no-go. We avoid them completely.
But the risk calculation changes later in pregnancy.
It does. In the second and third trimesters, if a mother has a really heavy hookworm load, she might be severely anemic. Hookworms literally drink blood from the intestinal wall.
And severe anemia is dangerous for both the mother and the baby. It can kill mothers. It causes low birth weight.
Right. In those specific cases, the WHO guidance is clear. Treat the mother. The immediate known risk of the worm, the anemia, the malnutrition, is greater than the theoretical risk of the drug to the fetus at that later stage.
It's a stark reminder that medicine is rarely black and white. It's all about weighing hazards.
Always. It is constant risk management.
Let's pivot to the second class of drugs, the macrocyclic lactones. The star here is, of course, ivermectin.
A drug with a Nobel Prize attached to it, and deservedly so. It has saved millions from blindness.
And it has this weird origin story, something about a Japanese golf course.
That's right. The scientist Satoshi Mura was just screening soil samples. He found a bacteria, Streptomyces evermiddlis, in a soil sample taken near a golf course in Japan. He sent it to his partners at Merck for testing, and they discovered it produced these incredible compounds, the ivermectins, that were just devastatingly effective against worms.
So benzimidazoles break the skeleton. What does ivermectin do?
Ivermectin is a paralytic, but it doesn't work on the same channels we usually talk about in human neuromuscular pharmacology. It targets glutamate-gated chloride channels.
Okay, let's break that down. A channel in the cell membrane that opens when the neurotransmitter glutamate hits it, and it lets chloride ions in.
Right. Now, in the worm, these specific channels are found in their nerve and muscle cells. When ivermectin comes along, it binds to them with incredibly high affinity, and it forces them open. It essentially locks the gate in the open position.
So chloride just floods into the cell.
Chloride is a negatively charged ion. So when it floods into the cell, the inside of that cell becomes extremely negative. We call this hyperpolarization.
And chemically, a hyperpolarized nerve or muscle cell cannot fire an action potential.
Exactly. A nerve needs to become positive. It needs to depolarize to send a signal. If it's hyperpolarized, it's pinned down electrically. It's silenced. The result is atonic paralysis. The worm freezes.
But it's not just about movement, is it? It's about feeding, too.
No, that's a great point. These worms have a pharynx, a kind of throat, that actively pumps food in. Ivermectin paralyzes the pharyngeal muscles, too.
So it can't move, and it can't eat.
It starves, and because it can't cling to the tissue or swim against the flow of, say, the gut or the bloodstream, it gets flushed out by the host's system.
Okay, time for the selective toxicity check again. Humans use glutamate. It's our primary excitatory neurotransmitter in the brain. If ivermectin is forcing glutamate channels open, why doesn't it just shut down our brains?
Two really important reasons. First, we don't really have these specific glutamate-gated chloride channels in our peripheral nervous system. That's an invertebrate-specific channel. We have GABA channels, which are structurally similar, but ivermectin binds them much more weakly, about 100-fold lower affinity, so it mostly ignores our peripheral nerves.
So that's the first reason. What's the second?
The second is the big one. It's an anatomical wall, the blood-brain barrier.
The bouncer at the door of our CNS.
The best bouncer there is. Ivermectin is a large lipophilic molecule, but there is a pump in the blood-brain barrier called P-glycoprotein. Its job is to recognize foreign molecules like ivermectin, grab them, and actively throw them back into the blood.
Like an ejector seat.
A very efficient ejector seat. P-glycoprotein is incredibly good at keeping ivermectin out of the human brain.
So we are safe because of a pump.
We are, which leads directly to a critical contraindication. If that barrier is broken, say in a patient with meningitis, or if that pump is overwhelmed or inhibited by another drug, ivermectin can get in.
And if it gets into the brain?
Then it will hit our GABA receptors. And the result is profound CNS depression. We're talking sedation, ataxia, coma, and even respiratory failure.
And there's a specific warning about African trypanosomiasis, sleeping sickness, in the text.
Right. Sleeping sickness is a disease that directly disrupts the blood-brain barrier. The parasite itself basically breaks the seal. You absolutely do not give ivermectin to a patient with active CNS trypanosomiasis. It's far too dangerous.
Let's talk about the killer app for ivermectin. River blindness, onchocerciasis.
This is a true human tragedy caused by a filarial worm, Onchocerca volvulus, which is transmitted by black flies that breed in fast-flowing rivers.
Hence the name.
Hence the name. The adult worms live in these nodules under the skin, all twisted together, but the real devastating damage is done by their babies.
The microfilariae.
Millions of them. The female worms release millions of microscopic larvae that migrate throughout the skin. They cause an absolutely maddening, intense itching, but tragically, they also migrate into the eyes.
And it's the immune reaction to the worms dying in the eyes that scars the cornea.
And that's what causes the blindness. It has wiped out the productivity of entire communities in West Africa. Ivermectin completely transformed this disease. A single dose clears the skin of microfilariae with incredible speed. It stops the itching, and it prevents the eye damage from progressing.
But, and this is a huge but that the texts emphasize, it doesn't kill the adult worms?
No. This is a key point. It is microfilaricidal, it kills the babies, but it is not macrofilaricidal, it doesn't kill the adults.
So the parents are still alive in that nodule under the skin.
And they are still fertile. So a few months after the treatment, the babies start to return.
So you have to keep treating over and over.
Once a year, every single year, for the entire lifespan of the adult worm.
And how long is that?
It can be 10 to 15 years.
15 years. Wow. So this isn't a cure. It's suppression. It's a very long-term commitment.
It is. But if you can treat the whole village every year for 15 years, the adult worms eventually die of old age. And critically, because the microfilariae are gone from everyone's skin, the black flies have nothing to pick up when they bite.
You break the transmission cycle.
You break the cycle.
Now let's talk about the side effects. Because this is fascinating. The side effect often isn't the drug poisoning the person. It's the person reacting to the victory.
The Mazzotti reaction. This is so crucial to understand. Imagine you have millions, literally millions, of microfilariae crawling through your skin. You take a dose of ivermectin, within hours, they all die simultaneously.
It's a mass casualty event happening in your own skin.
Exactly. Their tiny bodies start to decay. They release all these foreign antigens. The immune system wakes up and just goes, what is all this foreign protein? And it goes nuclear.
And the patient feels it.
Oh, they feel it. Fever, headache, dizziness, swollen lymph nodes, a terrible rash, tachycardia, sometimes hypotension. It can look like a severe allergic reaction or even sepsis.
But it's not an allergy to ivermectin.
No, it's an inflammatory storm triggered by the dying worms.
So, in a strange way, feeling absolutely terrible means the drug is working.
Clinically, yes. We often have to give supportive care, like antihistamines or mild steroids, to manage the reaction. But there is one scenario where this reaction goes from just being miserable to being deadly. And that's with the Loa Loa worm.
The African eyeworm.
Right. Loa Loa is another filarial worm found in Central and West Africa. But unlike Onchocerca, the microfilariae of Loa Loa circulate in the blood. And in heavy infections, in massive numbers.
How massive?
We are talking tens of thousands per milliliter of blood. A staggering bioload.
I can't even imagine that.
So if you give ivermectin to someone with that high parasite load, the rapid killing is absolutely catastrophic.
Why? Is it just a much bigger Mazzotti reaction?
It's the location of the die-off.
Yeah.
The massive release of antigens and cellular debris can trigger capillary blockage in the brain or massive cerebral inflammation. It causes a severe encephalopathy.
So they can go into a coma?
They can go into a coma and they can die.
That's terrifying. So if you're running a mass drug administration campaign in a village in Cameroon to treat river blindness, and you just hand out ivermectin to everyone,
you could accidentally kill someone who has a heavy, undiagnosed Loa Loa infection.
that's a major public health challenge.
It's a huge logistical hurdle. In areas where both river blindness and Loa Loa exist, what we call co-endemic areas, you have to screen people first. You have to check their blood for Loa Loa before you can safely treat the river blindness.
It adds this whole other layer of complexity to what should be a simple pill distribution program.
Complexity is the hallmark of parasitic disease. It's never simple.
Let's move on to our third weapon, praziquantel. This is the big gun for flukes and tapeworms.
The calcium flood, as I like to call it.
And the text admits something really interesting here. We don't know the exact molecular binding site with 100% certainty.
Right, and that's not uncommon in pharmacology. We often know what a drug does, the physiological effect, long before we identify the specific receptor it's binding to. We know that praziquantel causes a rapid, massive influx of calcium ions into the worm.
And in muscle physiology, calcium equals contraction.
Spastic paralysis. The worm goes into tetany. It cramps up violently and immediately.
Okay, let's contrast that with ivermectin. Ivermectin was a flaccid paralysis. The worm went limp. Praziquantel is a spastic paralysis. The worm goes stiff.
Exactly. Now, why does this matter? Think about schistosomiasis. These are blood flukes. They live in your mesenteric veins, or the veins around your bladder, and they have to hold their position against the constant flow of blood using these powerful suckers.
Like a mountaineer hanging onto the side of a cliff.
A perfect analogy. Now, if that mountaineer suddenly has every muscle in their body cramp up and go rigid,
They let go. They fall.
the schistosome loses its grip on the vessel wall. The blood flow just sweeps it away, gets washed downstream into the liver. But that's where praziquantel has a second, equally important mechanism that kicks in.
Okay.
It damages the worm's tegument.
The worm's skin.
Right. And schistosomes are masters of disguise. They cover their skin in host proteins, your blood antigens, to look like you. They are essentially wearing an invisibility cloak to hide from your immune system.
Clever.
Praziquantel causes what's called vacuolization of this tegument.
It makes it bubble.
Yes, exactly. The skin bubbles and bursts. It blows their cover completely.
The disguise is ripped off.
And the worm's own antigens are exposed for the first time. And now, the host's immune cells that are waiting in the liver, the granulocytes, the eosinophils, they swarm in and destroy it.
So praziquantel first knocks them off the wall, and then it paints a giant target on their back for the immune system.
It's a brilliant one-two punch. It's highly effective. But we have to talk about that drug interaction with steroids again. Remember albendazole?
Yeah, they were best friends. The steroids boosted the albendazole levels.
With praziquantel, it is the exact opposite. Dexamethasone induces the liver enzymes, specifically the CYP450 system, that metabolize praziquantel.
So if you give steroids,
The liver chews up the praziquantel much, much faster.
so the drug levels in the blood drop.
Significantly, sometimes by as much as 50%.
That is a dangerous clinical trap. You have a patient with neurocysticercosis, the brain's cysts. You give them steroids to control the swelling. If you chose albendazole as your anti-worm drug, you're winning. But if you chose praziquantel, you might be accidentally underdosing them because of the very steroid you need to give.
Exactly. And this is one of the main reasons why albendazole is now generally preferred for treating neurocysticercosis. The pharmacology just aligns better with the necessary supportive care.
Plus, the text mentions a very practical, almost funny side effect of praziquantel, the taste.
It is legendarily bitter. It is one of the most unpleasant tasting drugs in the pharmacopoeia.
So the advice is,
Swallow the tablet whole. Do not chew it. Do not even let it sit on your tongue. If a patient chews the tablet, the bitterness is so intense it can cause immediate violent retching and vomiting.
the pucometer effect, as one professor called it.
A simple but absolutely crucial clinical instruction. If they vomit the pill, the treatment has failed.
Okay, let's look at our fourth player. Diethylcarbamazine, DEC. This is an old drug.
Very old. Developed in the late 1940s, it's a derivative of piperazine, and frankly, if you look in the texts, the mechanism is still listed as unknown or incompletely understood.
How can we use a drug for over 70 years and not know exactly how it works?
Well, we know that it works. And we know a key feature. It absolutely requires the host immune system to be effective. If you put DEC in a petri dish with microfilariae, nothing happens. They just swim around happily.
So it's not a direct poison. It needs the body to work.
It seems to alter the surface of the microfilariae again, this theme of exposing them. It sort of paints them for destruction by the immune system. It also seems to disrupt their arachidonic acid metabolism, which might stop them from producing molecules that suppress the host's immune response.
So it's an instigator. It breaks the truce between the worm and the host.
It is. It starts the fight. And it's the drug of choice for lymphatic filariasis, the worms that cause the horrible swelling of elephantiasis. But there is a massive red flag with this drug, a huge do not cross line.
And let me guess, it has to do with river blindness again.
You never, ever, under any circumstances, give DEC to a patient with onchocerciasis.
Why? I mean, ivermectin causes the Mazzotti reaction, but we still use it. Why is DEC so different?
Because DEC is too good, or rather it's too violent. It kills the microfilariae in the eye instantly and explosively.
It's a bigger, faster grenade.
Much bigger. The resulting Mazzotti reaction in the eye is so severe that it causes something called sclerosing keratitis. It scars the cornea permanently and opacifies it.
So you could blind the patient with a single dose.
Exactly. You are trying to save their sight, but the very drug you use blinds them. Ivermectin is a slower, gentler killer in the sensitive environment of the eye. DEC is just too dangerous. So again, before you treat for elephantiasis in Africa, you have to be sure the patient doesn't also have river blindness.
The geography determines the pharmacology.
Always. You are treating a patient in their context, not a disease in a vacuum.
Okay, let's hit a couple of the minor agents mentioned. There are some hidden gems here. Parantel, Pomote. This is the stuff you can buy over the counter at the drugstore.
Reese's pinworm medicine. It's that yellow liquid that tastes like chalky bananas. Any parent of a young child probably knows it well.
How does that one work?
It's a depolarizing neuromuscular blocker. It acts like a massive overdose of acetylcholine at the worm's neuromuscular junction. It stimulates the nicotinic receptors on the worm's muscle cells and doesn't let go.
So spastic paralysis again, like praziquantel.
Yes. It locks the muscle in the on position, the worm cramps up, loses its grip on the intestinal wall, and the gut's normal peristalsis just pushes it out. And since humans absorb it very poorly from the gut, it's incredibly safe. It kills the worm where it lives and leaves the kid alone.
Simple, safe, and effective. But the one that really blew my mind when reading for this was doxycycline.
Ah, yes. the antibiotic.
We use this for acne. For Lyme disease, why in the world are we talking about it for worms?
This is one of the most beautiful stories in pharmacology. It's a story of Russian nesting dolls. It turns out many of these big filarial worms, like Rucheraria bancrofti, which causes elephantiasis, and Onchocerca, which causes river blindness, they have a bacteria living inside their cells.
Wait, a parasite has its own parasite?
An endosymbiont, a bacteria called Wolbachia. They are partners. The worm has evolved over millions of years to depend on this bacteria for essential metabolic products, possibly things like heme or certain nucleotides. The worm cannot reproduce, and in many cases cannot even survive long-term without its bacterial partner.
So the strategy is ignore the worm and kill its bacteria.
Precisely. You give a long course of doxycycline, 4 to 6 weeks. You wipe out the Wolbachia population inside the worm.
Bear myself.
The female worms become sterile. They stop producing babies, and eventually the adult worms die prematurely. It is a true macrophyllaricidal strategy.
That solves the ivermectin problem. Ivermectin only killed the babies. This strategy eventually kills the adults.
Yes. And because the death of the adult worm is slow, it happens over months, you don't get that violent, dangerous Mazzotti reaction. You don't get the eye damage or the brain swelling. It's a stealth attack.
That is just incredibly elegant. It shows how deep our understanding of these complex life cycles has to be to find these vulnerabilities.
It changes the paradigm completely. It moves from poison the pest to disrupt the ecosystem.
Let's zoom out now to the public health level. The sources talk a lot about MDA, mass drug administration.
This is pharmacology at a scale that's hard to comprehend. We aren't just treating individual sick patients, we are treating entire populations. The WHO estimates that in 2014, 853 million people took these drugs.
Nearly 1 billion people in a single year. That is a mind-boggling number.
And the goal isn't just to cure the person in front of you. The strategy is called preventative chemotherapy. You go into a village where these worms are common, and you treat everyone, sick, healthy, young, old. Everyone gets the pill.
To wipe out the entire reservoir of the parasite in the human population?
Exactly. If you dramatically lower the worm burden in everyone, the vectors, the mosquitoes, the flies, the snails, they can't find any larvae to pick up when they feed. The cycle breaks. We're trying to drive these ancient diseases to local extinction.
But when you use drugs on that kind of scale, nature almost always fights back. Resistance.
It is the looming shadow over all of this incredible progress. In veterinary medicine, in sheep and cattle resistance is already a full-blown catastrophe. Farmers treat their herds so often that benzimetazoles and ivermectin are failing in many livestock populations around the world.
And are we starting to see it in humans?
It's emerging. We are seeing reduced efficacy of ivermectin in some river blindness populations in Ghana. We're finding genetic markers for benzometazole resistance in hookworms from various places. We are in an arms race, and we are putting immense selective pressure on these organisms.
If we lose these few classes of drugs,
we don't have many backups. The pipeline for new antihelminthics is very, very dry compared to antibiotics or cancer drugs. There just isn't as much profit in developing a drug for the world's poorest populations.
Which makes stewardship of the drugs we currently have absolutely vital.
It's paramount. And it's why we increasingly need to use combinations polypharmacy, giving albendazole plus ivermectin, or albendazole plus DEC. It's much harder for a worm to evolve resistance to 2 different mechanisms of action at the same time.
Okay, let's try to synthesize all this. We've covered a lot of chemistry and biology, but it really seems like there are 3 main ways to kill one of these giants.
I think that's a great way to frame it. 3 core themes of attack. 1, attack the architecture. That's the benzimetazoles, like albendazole. Break the microtubules, starve the cell, dissolve the fundamental structure.
2, attacks the movement.
Right. That's the paralytics. Ivermectin causing a flaccid paralysis via chloride channels, and parantel or praziquantel causing a spastic paralysis via nicotinic receptors or calcium. If they can't move, they can't feed, and they can't stay.
And 3, attack the defense.
That's the most subtle one. That's DEC and praziquantel ripping off the antigenic disguise, or doxycycline removing the worm's bacterial ally, unmasking them so that the host's own immune system can finally do its job.
And the red thread that runs through all of this, the concept you started with, is specificity.
Selective toxicity. We are exploiting the ancient evolutionary differences. The fact that their tubulin is slightly stickier to the drug than ours, the fact that they have a glutamate-gated chloride channel that we just don't. That is the only reason any of this is possible.
The Peruvian shepherd we started this whole hour with, he got albendazole, probably with a very fatty meal. He got surgery. He survived.
100 years ago, that diagnosis was a slow, inevitable death sentence. Pharmacology completely changed the ending of his story.
And that really is the power of this science. It's not just about molecules and receptors. It's about pulling monsters out of people.
Well said.
I want to leave the listener with one final, slightly provocative thought. We talked about how these worms have been with us for millions of years. We co-evolved.
Indeed, we grew up together, evolutionarily speaking. Our immune systems trained on each other.
And that leads to the hygiene hypothesis, the idea that our immune system expects to fight worms. It has a whole arm, the IgE system, eosinophils, that is basically designed for this one war.
And when that war suddenly ends, when we kill all the worms with modern sanitation and effective drugs,
The army gets bored, it gets restless, and maybe it starts attacking things it shouldn't, pollen, peanuts, our own tissues. There's a very strong epidemiological correlation between the disappearance of worms and the dramatic rise of autoimmune disease and allergies in the developed world.
it's a very compelling theory. So compelling that we are now running clinical trials of therapeutic Helminth, intentionally giving people pig whipworm eggs to treat Crohn's disease or multiple sclerosis, trying to restore that ancient balance.
So maybe in the future, the deep dive will be about which worm you should be prescribed to cure your asthma.
Let's not throw away the albendazole just yet. But yes, it's a reminder that biology is always more complex than we think.
For those who want to see the dosage tables, the chemical rings, and the detailed pharmacokinetic graphs, you have to go to the source. Goodman and Gilman, Chapter 55 on chemotherapy of Helminth infections, and Cutzon, Chapter 53.
We gave you the conceptual map. You really have to walk the territory yourself.
Thanks for listening. Stay curious. And please, for so many reasons, wash your hands.
Absolutely. Wash your hands.